Well, thanks so much, Parth, and thanks again, everyone, for coming. Yeah, as Parth said, this is something we've talked about doing for years, and I'm really glad we're finally doing it. Get to meet all of you guys in person. Yeah, I'm going to talk briefly about how CVXPY came together. I'll start for the maybe more for the audience online about what a convex optimization problem is. This is sort of a generic standard form that you can imagine where you're minimizing some convex function f naught of x, and then you have inequality constraints where these fi's are convex, and then you have linear. And this, it turns out, is a really useful class of optimization problems that you can solve very efficiently and reliably, but that cover a very wide range of applications and have a very broad. Now, given that you want to solve a convex optimization problem, how do you do it? Well, the solvers generally are designed for particular standard forms, such as a linear program or quadratic program. And in order to solve your problem using one of the solvers, you have to convert it into that standard form, which can be a complicated process, very error prone. Another approach is writing your own solver, and this can be beneficial when you have special structure, maybe you have some enormous problem that you want to distribute across many machines. But it's obviously a lot of work, expertise. And the third option, which CVXPY represents, is using a convex modeling language, which gives you a user-friendly way of describing the problem, and then behind the scenes is converting it into the same. Now, CVXPY is based on CVX, which is kind of the original version of original convex model language from Stephen Boyd's lab. And it was developed by Michael Grant around 2006. It's in that lab. And it looks, this is an example problem. So you have CVX begin and CVX end, and then you define the problem in a nice syntax, and then it takes care of everything else behind the scenes. And I remember using this quite a bit when I was first learning convex optimization. Really appreciating how easy it was. Michael Grant, in the course of developing CVX, he developed this idea of disciplined convex programming, which I think of as the type system for this language, this domain-specific language. And essentially, it's a type system that verifies the convexity properties of the functions. And it's a sufficient condition for convexity, but not necessary. But it's not restrictive in practice. It's a really nice design that has worked very well. And one aspect of the design is boiling all the rules about what's convex, how you can combine different convex functions into one single rule, which I'm not going to go into detail about this, but I thought this is a really nice approach because first of all, the rule is like not relatively human interpretable, so you can look at your problem and think about it. But more importantly, you can. It's very nice for automated analysis because you're just parsing going up into the expression tree, applying the same rule again and again. Now, CVX was really amazing software and extremely widely used. When I started working on this was about 2013. There were a few things that Stephen highlighted as areas for potential improvements. One was using sign information. CVX had a lot of differentiation between, like, there was a square function and a square pause function if the argument was positive. So if you use the sign information, you have a tighter type system. And so that was one thing. Also, there had been a lot of work, which I'll discuss very briefly, about parameterized problems. So we wanted to have parameters in there that would somehow hash something. So if you solve multiple problems again and again with the same structure, but slightly different problem inputs, there would be some amortization of that work. And then I had done a lot of programming in Python, and I thought that this code block approach made sense in MATLAB, but it wasn't very Pythonic. I wanted to have a more expressive way of, or more flexible way of describing problems. And then, in the interest of time, I'll go through this briefly. Related work, CVXGen by Jacob Mattingly in 2012. This is actually used by SpaceX, which is very cool. And it's very focused on parameterized problems and generating customized solvers. There was also work by Eric Chu called QCML, which was sort of similar to CVXGen, but you defined your problem as a string in Python. So it was still not embedded in Python. But it was, yeah, it was. I think that was something. This is a library that CVXPY took a lot of inspiration from as well. And then there was also some other attempts at a Python version of CVX, like CVXMOD. So I started working on the project, as I said, in 2013 when I was an undergrad. My actual very first project for Stephen was dcp.stanford.edu, which is this website that teaches you the DCP rules. And yeah, the goal was essentially create CVX, but in Python, and including parameters, and then having it be more Pythonic. This is the very first CVXPY example ever, and it has not changed too much from the user's perspective. It still looks more or less like this, which I think is nice. It's changed a lot on the inside, many refactors, but the core idea of the interface is the same for all the teams. And then just one brief note, the parameters, it took us a long time to really figure out what to do with these. And it actually led to some interesting divergence from how CVX worked. CVXPY ended up much more focused on expression trees, which was something that I looked at during my PhD and different, for example, with matrix-free algorithms. And I think the parameters finally fulfilled their potential in CVXPY layers and CVXPY Gen. We developed this nice idea called disciplined parameterized programming. And we're able to really get, I think, have a satisfactory approach to parameters. But that took many years. All right, well, going on to Will.